Hey there, my name is Trevor Gu, and here's my creative project number 3. Today I will be discussing how to experimentally determine the Young's modulus constant, which is E. So in terms of the exploration, what I'll be doing is determine the E value of different infill percentages of a 3D printed beam. So in terms of the beam, it will have a square cross-section, it's going to be made of PLA, and has a cubic infill. And I chose this pattern because it's generally recognized as the best in terms of strength and efficiency for FDM printers, which is what I will be using. And the length of the beam will also be constant. In this exploration, I will also simulate a fixed beam with a point load P at the end. So it will look similar to the diagram right here, with a fixed side and a free end with the force at the very tip. So in terms of prerequisite knowledge, what is E? E is the Young's modulus, which is the modulus of elasticity, or in other terms, it's the measure of an object's stiffness. So to better visualize it, the higher the E value, the more stiff the object will be. And so my prediction will be as the infill increases, the beam will become less bendy or more stiff, and so the E value will also increase. So in terms of prerequisite equations, I will be using the bending moment displacement equation. This basically states that the moment over the E value times the moment of inertia is equivalent to the partial derivative of the displacement relative to x. And I don't want to derive the equations just due to time's sake, but you have you basically take the double integral of this side of the equation. So you have the starting moment, which is P, which represents the force, times L, which represents the length of the bar, minus x. And x is the location where you're trying to find the displacement. And then basically you integrate it twice, and you end up with this equation right here. So in terms of procedure, I will first CAD and 3D print beams of varying infill percentage. And then I will set up the fixed beam environment, and then place the point load at the end of the beam for max displacement. And that's just to better visualize and get the best results. And then for step 4, I will measure the displacement at different points along the beam. And then I will use MATLAB and derived equations to solve for the average value of E. So in terms of execution, the first step is to CAD and slice this. So here's me slicing it, slicing the 5% beam. I believe this is the 15% beam, and then you have the 10% beam that is actually printing. So in terms of the setup, first off, we have the block, which represents the fixed end of the setup. That's just held by these two beams, and I'm pushing down on it to simulate a fixed environment. And so we have a parallel beam relative to the ground, and then you have an infilled beam. I believe this is the 5% beam right here. And then you have the length markings where I will measure the displacement, and the displacement is basically the distance between the parallel beam and the infilled beam. And the length markings represent where I'm going to measure the displacement. So there's also a marking down over here, you can't really see it. And then you have the payload right here. So in terms of the values obtained, the length of the beam, or L, is 25 centimeters, but because it's on this block over here, I have to subtract 1.9 centimeters off it, so the length turned out to be 23.1 centimeters. The width of the beam is 1 centimeters, and the payload is 88 grams, and if you convert that into in terms of newtons, it will be 0.8633 newtons. And so in terms of the raw data, for the infill percentage at 5, for 5%, the displacement was max at the end, which is 1.6 centimeters, so right here. And then at 5 centimeters from the end of the bar, it was 1.1 centimeters, and then 10 centimeters, it was 0.8. And then as you can see, as you increase the infill percentage, the displacement decreases. So in terms of solving for E in MATLAB, I first have to calculate the moment of inertia for each beam, and it's different because each beam has a different infill, and I'll get into why later. And then I will also have to find the average value, find the value of E at each position, and then average those 3 values. So here's just the start of my code. We have the 4 values that are common for each beam. So in terms of the code, the only values that are extremely important are basically the dn value, which represents the displacement at each position, and it's represented as a vector. Then you have the percent of the beam, and then you have the moment of inertia of the beam. And so this is done by basically assuming that the beam is a hollow square cross-section. And so I already sort of derived these equations, and basically this E5 value represents the E value at 5%, and what we have here is 4.639 e to the 8. So in terms of the results and conclusion, my predictions were correct. As infill increases, the moment inertia increases, and the E increases. So the infill percentage, as you can see, when it increases, the E value, or the stiffness, also increases. So what we have is at 5%, it was 4.64 e to the 8. 10% 7.13, and then 15 16.67. So in terms of an accuracy check, the value of E for PLA is 3.4 gigapascals, or 3.4 e to the 9 pascals. And this basically assumes that the bar is infilled at 100%. So a possible continuation of this lab, or this experiment, is to determine the E value at 100% infill. And in this one, I only figured it out, right, at 5%, 10%, and about 15%. And so my prediction is that the infill, in terms of the infill versus E, it will plateau to about 3.4 e to the 9 pascals, or when it's at 100%. And that's because, like around 50% it will start to plateau, and that's because after a certain amount of infill, 50% to 100%, the elasticity of the bar remains the same. So pretty much after 50% to 100%, you can't really tell the difference in terms of rigidity. So in terms of possible errors, there were a couple errors at play. Perhaps taking measurements or simulating a fixed free beam. Perhaps my finger might have slipped when I was measuring or something like that. In terms of the generalization for moment of inertia, I did this because the infill pattern changes. And so I use a generalization because it'd be really hard to create a super accurate moment of inertia representation due to the cubic nature of the pattern. And so basically what happens is it treats the mass, it treats it like all the mass on the outside and the beam is hollow. So what I mean by that is that if you have 100% infill, then obviously there's no hole. But if you have a 60%, you have a small hole. And then if you have 50% infill, which is what I had at one point, there will be a large hole. But all the mass you can see is concentrated on the outside. And so thanks for watching.